Mr. Allred here, and I'm going to talk about directional derivatives a little bit. So we already know that if you have a multivariable function that if you move in different directions, the slope or the function will change at different rates. So when we say directional derivative, we're talking about taking that function f and then picking a direction we want to move, not just in the x or y axis direction like I and j, but in any direction, even any three-dimensional direction. We do want this u to eventually be a unit vector. It may not be given to us that way, but we're given a function and we need a place, but we're given a direction to move, and the directional derivative will calculate the derivative, of course, which is the rate of change in that direction. So notation here is big D sub UF. So the big D means directional derivative, the sub U means the direction that we're moving in, and F, of course, is the function. We're going to be given a point. So the calculation is going to be the gradient of the function at that point times that unit vector direction. Okay. So let's see here. What can we do? Okay, we've got an example here. It's f of x equals 2x squared plus y squared. The point is negative 1, 1, and the direction is 3i minus 4j. So first of all, let's get our gradient, which will be 4xi plus 2yj. So that's the partial of f with respect to xi plus the partial of f with respect to yj. And then we need to evaluate that at the point we were given negative 1, 1. So we will have a definite gradient. So that will give me negative 4i plus 2j. So that's the gradient. Now, the direction we were given here was 3i minus 4j. So let's find the magnitude and divide that out. So the magnitude of 3i minus 4j is the square root of 3 squared plus 4 squared. That gives me 25. Square root of 25 is 5. So the u that I will use here will be 3/5 I minus 4/5 j. Alright. So that is the u. That's the direction we're going to move. So we've got f at a point and we've got direction. So let's see here. So we're going to say d of uf at this point is going to be the dot product of negative 4 to 3/5 negative 4/5. So let's see. That's going to give me negative 12/5 minus 8/5. So negative 20/5 gives me 4. Okay, I'm going to pause for just a second. Okay, I'm back. I was gone for a little while, but you were gone just for a second. Actually, this is negative 4. I saw that as soon as I stopped it. So the directional derivative there is a number because this is the dot product of the gradient, which is a vector direction, and the direction we're picking, u. Alright, so let's see here. I got another example down here we're going to do. So this one here, we've got f of xyz equals xy plus yz plus zx. So let's see. First of all, we're going to do the gradient of that. So the x direction will be, the I part of the gradient will be y plus z. The j part will be x plus z. And there's a k part in this one, which will be y plus x. And now we need to plug in our point, which is 1, negative 1, 2. So let's see, if that's the case, 1, negative 1, 2. So the I part will be 2 minus 1, so that'll just be 1I. The J part will be 1 plus 2, so that will be plus 3J. And the K part will be X plus Y, so that'll be 0K, which I'll throw away. Then separately over here, the direction we're going to move in is 3I plus 6J minus 2K. So the magnitude of that is the square root of 9 plus 36 minus 4. So what is that? Not the best, is it? Let's recount here. 9, 36, plus 4 when we square the negative 2. So that is 7. So the U I'm going to use is 3/7 I plus 6/7 J minus 2/7 K. So the directional derivative of in the direction of U of F at the point 1, negative 1, 2 is the dot product of 1, 3, 0 and 3/7, 6/7, negative 2/7. So what is this? 3/7 plus 18/7 plus 0 equals 21/7 equals 3. What a nice set of numbers these came out to be. Alright, so that's a little bit of work, but really not that difficult with the functions we use. Now if we had some chain rules or some crazy product rules or some weird, well, I guess our U is going to be nice coefficients, but hopefully things work out this well in the future.